Good evening, 8-bit physics students. Here's got another example problem for you from Mr. Kirsten. And tonight we are going to be checking out chapter number 5, problem number 12. And I like this problem because it is going to make us use both circular motion and friction, getting into the combining ideas. So this problem reads, problem 12, a coin is placed 11 centimeters from the axis of rotation of a turntable of variable speed. For those of you who don't know, a turntable is a record player, and it's what Mr. Kirsten used to listen to music on back in the day. And this turntable, there's a coin, so it's like there's a coin on the record player, and the turntable is spinning. And when the turntable gets up to a speed of 36 RPMs, which stands for revolutions per minute, the coin slides off. So the turntable's spinning around and around. There's a coin on it. When the turntable gets up to 36 RPM, the coin falls off. What is the coefficient of static friction? Holy cow, how can we figure this out without knowing hardly anything? I guess one other thing it does tell us is that the distance from here to here, which I'm going to call R, is 11 centimeters, which that would be 0.11 meters. Okay, well, what is going on here? Let's start out with a free body diagram. And for my free body diagram, I'm going to look at this record from the edge. So here's my axis of rotation. Here is my coin. All right. The coin has a weight, which we're assuming is mg. It has a normal force, and it is actually the friction force that is causing the coin to rotate in a circle. Think about it. If there was no friction, this coin would just stay right where it is. It wouldn't spin at all. So it's actually friction that's causing the coin to rotate. In other words, the frictional force is the centripetal force. It is what is causing this coin to go around and around in a circle. So that's kind of this is the big idea. Remember, a centripetal force isn't a force in and of itself. It has to be caused by something. A centripetal force might be friction, it might be a tension, but centripetal means center-seeking force. In this case, friction is the center-seeking force. Okay, well, let's see if we can solve for mu here. In this case, we can see that the weight has to be mg, right? And the magnitude of the normal force has to equal the magnitude of the weight. So the normal and the weight are equal in magnitude and opposite in direction. And of course, we know that the friction force is mu times the normal force. So we could say that the friction force is equal to mu sub s mg. What else do we know? Well, we know the centripetal force must be the mass times the centripetal acceleration, right? That only makes sense. Okay, so let's combine these two, right? And say that since the friction force is equal to the centripetal force, right? I can say mu sub s mg is equal to m a sub cp. And lo and behold, how about that? The masses cancel out. So if only I knew the centripetal force that this coin, centripetal acceleration that this coin is undergoing, I think I would be in some business here, right? Basically, how this equation is going to end up is mu sub s just dividing by g on each side, right? Divide by g on each side, right? Is going to be equal to the centripetal acceleration divided by g. Well, let's go off to the side here and see if we can't figure out what this centripetal acceleration is. Well, it's got to be v squared divided by r, right? Let's see if we can figure out what v, the speed of this coin rotating is. Well, speed is distance over time. Let's consider how far, well, this guy's going 36 revolutions per minute, right? Well, so how far would it go in 1 minute? How far would it go in 60 seconds of time? Well, it would go 36 revolutions, right? How far is one revolution? Well, that would be 2 pi r, right? So if we plug in 36 times 2 pi times 0.11 divided by 60, all right? Notice this is in meters, this is in seconds. I would get a speed of 0.41 meters per second, okay? Take that, plug that in right up here, right? I will get 0.41 squared divided by 0.11, right? And I get a centripetal acceleration of 1.56 meters per second squared. Make sure I'm not off the page here, all right? All right, I've solved for the centripetal acceleration here. All right, why don't I take this and plug this in down here, and I am going to get that the coefficient of static friction is equal to 1.56 meters per second squared divided by 9.80 meters per second squared. Meters per second squared cancel out, and we get a coefficient of static friction of 0.16. All right, not too bad. What a great problem. I have to combine my knowledge of circular dynamics with friction, and of course I get to talk about turntables and old records. Great problem. And as your reward, young physicists, for watching such a great problem, I have a prop here from way back when. This is Mr. Kirsten's Jefferson High School, Mr. Kirsten's Jefferson High School Math Team Award. This is my junior high mathematics league Sigma Merit Award for my math team performance on the 9th grade math team at Jefferson with my math advisor, Mr. Montbryan. So there you go. Nice work, physicists. We will see you in class tomorrow.